Hi everyone! In this video we are going to go over hydrohalogenation of alkynes. Now previously we talked about hydrohalogenation of alkenes. So let's just review that reaction. So you might remember that if we start with an alkene and add HBr, we end up with the following product where bromine adds to the more substituted carbon. So this is called Markovnikov addition, where the bromine or the halogen adds to the more substituted carbon, and the hydrogen adds to the less substituted carbon. Okay, so what would happen if we did this to an alkyne? So let's say instead of a double bond on the end of the molecule, we have a triple bond. And then we add hydrobromic acid. Well, we talked about the mechanism of hydrohalogenation previously, so let's just step through that. So maybe the alkyne comes in, grabs the hydrogen from HBr, since it's partially positively charged, and then the shared electrons are left behind on bromine. So then we might assume that we end up with hydrogen adding to the less substituted carbon, and then we'll have a positive charge on the more substituted carbon. And this is actually called a vinylic carbocation. Okay, so then in the next step, we might assume that the leftover bromide ion comes in and bonds to that positive carbon, and then we get our final product, which is an alkene, and then bromine is bonded to the more substituted carbon. However, scientists found that their experimental studies did not match this mechanism. So for one thing, vinylic carbocations are not very stable. So since they are not very stable, we would expect that the addition of HBr across this double bond would be really, really slow. However, it's actually not as slow as we thought it would be. But additionally, looking at this mechanism we drew, we would assume this would be a second order reaction. So it would just depend on the concentration of the alkyne and HBr. But through kinetic studies, scientists found that this is actually a third order reaction, not a second order reaction, which is very interesting. So scientists determined that this mechanism for an alkyne is not correct. So alkynes actually go through a different mechanism than alkenes. So there's a new theory, and this has been backed up with experiments. There's a new theory that if we have a terminal alkyne, it will actually react with two hydrobromic acid molecules at once. And one will come in, oops, my pen decided to go bold on me. One will come in from below, and one will come in from above. So the rate law for this reaction is equal to some rate constant, which is determined experimentally, multiplied by the concentration of the alkyne times the concentration of HBr squared. So remember, to figure out the order of a reaction, you just add all of the superscripts together, and there is an invisible 1 next to the alkyne. So this would be an overall third order reaction. And this is verified through experiment. So the thought is that the bromine from the HBr on the bottom, that's going to attack the more substituted carbon in the triple bond. And then the less substituted carbon will attack the hydrogen in the other HBr molecule. And then the shared electrons in HBr up above will go to the bromine. So let's just draw the transition state and kind of see where bonds are being broken, where bonds are being made. So let's redraw the alkyne. And I'm just going to draw a double bond between the carbons for now, because one of the pi bonds is going to break during this process. Okay, so now we have one hydrobromic acid molecule down below, and the bond between hydrogen and bromine starts to break as the bromine forms a bond with the more substituted carbon. As a result, one of the pi bonds is going to break as well, and the less substituted carbon will start to form a bond with hydrogen in the other HBr molecule, and then the bond between H and Br will start to break. So during this whole process, oops, my pen went rogue on me. There we go. So during this whole process, the more substituted carbon ends up with a partial positive charge. And really that's just due to that bromine there. So this is more stable than a fully positive vinylic carbon. So the partial positive vinylic carbon is more stable. So this also kind of verifies this mechanism. All right, so then once all the appropriate bonds are broken and new bonds are formed, we get a double bond. So we get an alkene. And then bromine is now bonded to the more substituted carbon, and the less substituted carbon now has an additional hydrogen. So again, this is still Markovnikov addition. Okay, so what would happen if we added more HBr? So let's see what would happen if we had excess hydrobromic acid. So let's start with the following alkyne. Oh, and I'll just draw the hydrogen on the end. So let's say we add excess HBr. So we just have a bunch of HBr hanging out. And I'm just going to highlight the more substituted carbon as blue and the less substituted carbon as purple. That way we can kind of keep track of where everything is adding. Okay, so first we're going to add HBr across the triple bond, and this will end up forming a transition, or an intermediate. So we'll get a bromine added to the more substituted carbon. So that's Markovnikov addition. And then the hydrogen adds to the less substituted carbon, and this turns into a double bond. Now, because we have excess HBr, this alkene will be really hard to isolate. So I'm just going to draw parentheses around this to indicate that it's not really observed and you can't really isolate this. So we'll just write not observed here. So we'll add more HBr because we have an excess of it. And what do you think will happen? Where will that second bromine add? To the more substituted carbon again. So now we're going to turn that double bond into a single bond. And instead of just one bromine at the more substituted carbon, we have two bromines now. Now, we talked about this type of dihalide previously when we were discussing the preparation of alkynes. Is this a geminal dihalide or a vicinal dihalide? A geminal dihalide. Because the bromines are bonded to the same carbon. Now, speaking of preparation of alkynes, how could we go from a geminal dihalide all the way back to our alkyne? What was the reaction that we did? So we needed a really strong base in order to perform those elimination reactions. So we used sodium amide, and then that will also be mixed with some ammonia. And in the second step, we also needed to add a weak acid in order to reprotonate the alkynide ion. So remember, that strong base is so strong that it takes the hydrogen from the triple bond at the end. So then we have to add a weak acid in order to reprotonate it. And you can just use water for that step. All right. So this is really cool. We're kind of seeing a whole cyclic reaction here. You could go all the way from an alkyne to a geminal dihalide, and then back to the alkyne if you wanted to. All right, so you might be wondering, what if I want to add the bromine to the less substituted carbon? How do I do that? Well, we're just going to perform AntiMarkovnikov hydrohalogenation, similar to our alkenes. So recall in the previous chapter that if you have an alkene and you want the bromine in hydrobromic acid to add to the less substituted carbon, you need to use peroxides as well. And we just symbolize peroxides with ROOR, where the R's are some sort of alkyl group. Now, when we add the peroxides in, again, bromine will now add to the less substituted carbon, so it will add to the very end of that molecule. Okay, so what happens if we do the same thing with a triple bond? So let's say we have a terminal alkyne, and we add HBr in the presence of peroxides. Well, the bromine is going to add to the less substituted carbon, but remember, we are going to end up with a double bond. So we could end up with an E-alkene, where the higher priority groups are opposite each other. Oh. And remember, E stands for opposite. And then we could also end up with the Z-alkene, where the higher priority groups are on the same side of the double bond. So Z stands for same. Now, you don't have to know this mechanism just yet because it does involve a radical. So we'll talk about that in a later chapter. So I'll just write a note down here. This mechanism goes through a radical pathway. So we'll cover that later. All right. So just remember, if you add hydrobromic acid across a triple bond, you'll end up getting Markovnikov addition of that bromine. And it kind of goes through this mechanism where the alkyne is sandwiched in between two hydrobromic acid molecules. And then also remember that if you add peroxides, then the bromine will add to the less substituted carbon. But because we're going from a triple bond to a double bond, you can end up with a mixture of stereoisomers. So you'll get the E-alkene and the Z-alkene. Okay, so in the next video, we will also talk about acid-catalyzed hydration of alkynes. And we'll do a couple of practice problems as well, just so you can kind of see how that works with an alkyne. So I will see you then.